Hi, welcome to my YouTube channel. In this tutorial, we are going to understand Newton's law of cooling and how it is applied by the Ansys solver for modeling the convection. So let's start. We are going to double click on model. So the mechanical window has been opened. We can see here. So we can see this is the model here, and dimension we can see 1 meter this way and 1 meter this way. Thickness is 0.2 meter. So first we have to check this unit that is in metric, and if we go to project window here, engineering data also we can check that is concrete, and its thermal conductivity it is 0.72 watt per meter and degree centigrade or Kelvin. Now we are closing this one and coming to same in the mechanical window. Here we can see first we are going to generate mesh. Okay, now we can see here this convection. Convection is applied at this phase. It is having a film coefficient that is H 10 watt per meter square degree centigrade, and we have to enter this ambient temperature that is we have put here 30 degree. At the other phase, temperature has been applied that is 5 degrees centigrade. Okay, now we are going to solve this model. Solve. So it has been solved. We are going to insert thermal temperature and also click on these two things and drag to solution so we can get reaction probe on the surface. Now we are going to evaluate all results. So temperature we can see minimum 5 to 23.382. 5 is here and maximum will be on this face that is 23.382. If we go to reaction probe, here it is showing 66.176 watt heat, and on the other hand on the other face also minus 66176. So it's showing that it's like in equilibrium, thermal equilibrium. So now we have to check this heat calculation whether it is coming same by hand calculation or not. So let's start. First we have area that is 1 meter square, and film coefficient that is H, that we have 10 watt uh, per meter square Kelvin, and that equation we know that is Q equals to delta T upon R resistance that is convection. So where this RTH is equals to, for convection it is 1 upon HA. So here we have value of H and A, so this value will be 0.1 watt per meter. Okay. Now if you come to this problem, so then what we can see, so here this temperature that is 5 degree T1, and here that this surface temperature we do not have, that's TS, and convection, that temperature TF, we can take a TF, and that we have taken 30 degree. This is TF. Now it's a convection. Now surface temperature, this one. From here, then this is T1. This resistance is convection, and this resistance is conduction. So equation that comes is Q equals to T1 minus TF upon R thermal convection plus R thermal conduction. So from here we can get that whatever heat it is transferring from here to there in watt, and also that will be equals to T1 minus TS upon R thermal conduction and TS minus TF upon R thermal convection. So this equation we cannot use because we do not have surface temperature, this surface temperature. So we are going to use this one, and thermal, we have calculated this convection resistance, that is 0.1, and if we calculate for conduction, that will be L upon Ka. K is the thermal conductivity of the material, and that is given 0.72. So after putting this data, we will get this will be 0.27778. Now we are going to put all the details in this equation, that is 5 minus 30 upon, so convection 0.1 plus resistance for conduction, that is 0.27778. After solving, we will get minus 66.176 watt. So the same thing we have got in the analysis. So from here we have got this heat flow, that is minus 66, and if we want to get the temperature of this surface, then we are going to calculate T1 minus TS upon resistance for convection. So that we already have calculated 66.176. T1, it is, we can use this surface and this fluid. So TS, it is, we have to calculate TF 30 degree, and this is 0.1. So from here we can get temperature of the surface, that will come 23.382 degrees centigrade. So that you can see here. Thank you for watching. Please like and subscribe my channel.